In this video we're going to look at overfitting and underfitting. The idea is the following. If you run a regression like an OLS regression and you keep on adding variables to that regression, we've already seen that that's bad from the point of view of causality, because you're likely to misinterpret the coefficients that you're interested in by throwing in other variables. So we saw that in the examples of a collider and a pipe, where we kept on adding variables and then started to misinterpret the results that we saw on the variables that we were interested in. But here we're going to look at the fact that if you keep on adding variables, you're not hurting your interpretation in terms of causality, you're actually going to hurt your prediction. Your predictions will be getting worse. Now the first thing to observe is that when you look at an OLS regression, basically what you're doing is you're minimizing a loss function by the choice of your parameters, let's say beta, and your loss function will be something of the form we're going to sum the squared residual, so we sum over I, which is the observations that we have, so capital N is the total number of observations that we have. Then we have the observation yi of the variables that we're trying to predict or explain. And het y is actually going to be our prediction, or what comes out of our regression. And that's going to be a function of beta as well. And we're going to square this. Oops. So this is the regression that we'll be looking at. We're choosing this vector beta to minimize the sum of squared residuals. And usually it will be the case that with a linear regression, yi is going to be, het, our prediction is going to be a linear prediction. So I'm going to have a vector beta, so I turn it into a row vector and I multiply it by x. So that's the situation that we're going to be looking at today. So as you can see from this optimization problem, from this minimization problem, adding new variables x and coefficients beta can never hurt the loss function, because I can always decide to put these betas equal to 0. Yeah, so adding variables or adding coefficients beta will always reduce my loss function, and that will suggest that I'm improving the fit of my model. And that is actually not the case. So there are two things that I have to worry about. One is underfitting. So that's actually not including enough variables. So then the model doesn't predict as well as it could. And the other problem is overfitting, which happens when I keep on adding variables, which actually that shouldn't be there. And that's what's actually going to hurt our prediction. And the solution is that if you have enough data, you should make sure that you create a train and a test set. Yeah, so that assumes that your data set is big enough to actually do that. And I'm going to illustrate how that works in a simple example. And again, we're going to generate our own data, so we actually know how the data was generated. And then we're going to add variables that are irrelevant to the regression, and we're going to see that it's going to improve the results that we have, at least on the trained data. So I'm going to set the number of observations, let's say in this case equal to 30. So I'm going to create a trained set and a test set on our data. So let's say we do that half-half. So half the data, 15 out of 30, is going to be used for training the model, and then the other 15 is going to be used to test the model. Oops. So x is going to be a random variable, so random, let's say that we simply choose a normal distribution. The size of it is the number of observations. And if you want to get exactly the same results as I have, I can set a seed, so let's say seed is equal to 26. And I'm going to generate my variable y, and it's going to be equal to x plus 2 times x squared. Yeah, so that's it. So x is going to appear in this regression linearly as x and as x squared, but we're going to add a lot more variables, so you're going to see that in a second. Plus we're going to have some noise, so let's say so random, the noise is going to be normal as well. Number of observations, and again here I can set the seed equal to 50. We're going to create a data frame, so we're going to use pandas, pd, and then the method of the data frame. So data frame you create with creating a dictionary. So I'm going to have a variable column name x, and it's going to be equal to the variable x. I'm going to have a column name y, and it's going to be equal to the variable y that we just defined. So this will give me my data frame. I'm going to add some other variables to the data frame. So I'm going to add a constant to the data frame. And I say constant is equal to 1. So just to be clear, the data frame of course has a size of 30. And I'm saying here constant is equal to 1. So basically what pandas is doing here, it's using broadcasting. Yeah, so it will actually generate 30 ones to make up this column constant. And then I need to add some other variables as well. So we get data frame x2. It's going to be equal to, from the data frame x to the power, something that I will add in a second. So let's use 9 of these. So basically what I'm using here is an emacs macro, but don't worry about it. So I'm going to record another macro. I'm going to the end. I'm going to include this. So now I have added these variables here, x2, x3, x4, which is basically x to the power 2, 3, and 4, etc. I know from the way I generated the data that only x2 is relevant, and the variables x3 to x9 are actually completely irrelevant. But as we're going to see in a second, they still help to reduce my mean squared error. So now I'm going to create a data frame for my training data set, so that's going to be the data frame that I have. Oops, that's the wrong bracket. And that's going to be train size, and my test data is going to be from this data frame, train size till the end. Yeah, so just notice from a previous lecture what we're using here is slicing. So I'm saying here from the data frame train, take the data frame df and add all the rows from the beginning up to the point of train size, but not including row train size. And then the test set contains the row train size all the way up to the end. So I can run this. I don't get any errors, so that's positive. So then I can find my regression. So we'll start with the simplest regression that we can do in this case. So we're going to say that y depends on x only. And I'm going to create a list, which I'm going to call vector of results. Yeah, so I'm going to have square brackets for the list, and what the list contains is, again, we're using stats models, so we're using OLS on regression, and data is going to be equal to my train data set, and then I'm using the fit method on this. So I get vector results actually contains the fitted models that we have. So this is the first one, and then we say for column in df columns. Again, I'm using slicing here. Yeah, so just, if you wonder what I'm doing here, just run this part, df columns, without the indexing after it, separately in a cell, just to see what it is. And then you see why this is going to work. So this is going to be a regression, is equal to the previous version of regression. So the first time when we go through this loop, it's simply going to be this. But every next time that we go through the loop, of course, it's going to be a bit more than this, because we're going to add variables, and we're going to add a variable column. So basically what's going to happen is that when we run through these columns, I'm going to add the variable x2, x3, x4, all the way up till x9. And then we take vector results, and we're going to append to that. And again, we use OLS from stats models. We're going to run it on regression. The data is again going to be df train. And we apply the fit method to this. I need another bracket, I think. Yep, that should work. So let's see whether we didn't make any mistakes. No, it seems to work. Oh, sorry. So now I can plot the mean squared errors that we have found. So that's going to be from TensorFlow. I'm going to use Keras. And then I'm going to be interested in losses, and in particular in the mean squared error of so I take my training data set, and from that the thing that I want to predict is actually the column y from this data set, and the thing that I'm comparing it with is model predict of df train to make it a bit easier to work with. I'll use the numpy method on it. And this model here, so the model here, model predict, that model is going to run over the models I've defined in my list vector results. So I'm going to close this and I'm going to close that. I can then add a y label, because the thing that I'm plotting is the mean squared error. Oops, plt.show. And this is the graph that I get. So as you can see, the simplest model that we have is the first one with the 0 here. So that's our base model where we just regress on the constant and on x. And this is the mean squared error that I get. And then I'm going to add x squared, x3, etc., etc. And you can see that the mean squared error is going down. Although actually I know that these higher orders like x3, x4, x5 are completely irrelevant because we generated the data of y ourselves. Still, these irrelevant variables help us to reduce the mean squared error. So at the moment that looks fine, but the next step that we're going to do is to use the model prediction that we have on our test data and see whether we're going to see the same pattern, that the more variables we're adding, the better the result is going to be, in the sense that the mean squared error is going to be lower.